Welcome to the complex variable transforms course. In this lecture we will study Cauche Riemann's equations. These equations tell us that the function of a complex variable f of c, where c is the complex variable, it checks whether it is differentiable or not. Right. This function actually takes this z, a complex number, into another domain u and v, where we call this number as w. W is f of c. So we apply a function on a complex variable c and we move to another axis or another plane where the names of variables are u and v. This is what we studied last time, and in this lecture we will study how to find. First we have to check whether this function is differentiable or it is not differentiable. If it is, we will find its derivative with respect to c. So given this f of c, we are trying to find df of c over dz, and we see that the derivative exists everywhere if the Cauche Riemann's equations are satisfied. That otherwise it doesn't exist everywhere, it can exist on a certain part, right? So that will not cover. So we'll cover only if the case, only if it is if differentiable all around this function. W is u of xy plus j v of xy. In our last lecture we studied that this w can be written as, the real part of this w can be written as a function of x and y, and the imaginary part can also be written as the function of x and y. So if partial u over partial x is partial v over partial y, and this is second condition, that partial v over partial y is equal to negative of partial v over partial x, then f of z is differentiable. F of z is differentiable. This means that we can compute its derivative, and if it is differentiable, f derivative of c is partial u over partial x plus j times partial v over partial x, right? So this is how we compute the derivative f prime of z or df of z over dz only if f of z is differentiable. This derivative can only be computed if it is differentiable. And how would you know that it is differentiable? If these Cauche Riemann equations are satisfied, these two equations, if these two equations satisfied, the function is differentiable and we can compute its derivative, right? So we will solve an example where f of c is given to be z squared. F of c is given to be c squared. This f of c is w, the function of c. Right, and first we have to check whether it is differentiable or not. The task is to compute f prime of c, df over dz, but before that we have to write in terms of x and y, and then we'll apply these Cauche Riemann's equations to check whether it is differentiable. Right, so let's first write f of c in terms of x and y. We know that c is, we studied in the last lecture, x plus jy. So let's put x plus jy here, compute a square, and this is a squared plus b squared, a squared plus 2 times a times b plus b squared, right? So x squared plus j 2xy plus j squared, you know j squared is minus 1, so this is minus y squared. It can also be written as x squared minus y squared plus j times 2xy, where u is the real part of this w and v is the imaginary part. Right, so u is the real part of f of c, x squared plus x squared minus y squared, and v is the imaginary part 2xy. So let's compute partial u over partial x and these four partial derivatives to know whether the function is differentiable. So partial u over partial x is 2x minus the derivative of y squared. When we are computing derivative with respect to x, all other variables are treated as constants. So this is y squared is constant. So constant, the partial derivative of a constant is a 0. So it comes out to be 2x and partial v over partial y. Let's check whether these two are the same. write 2xy, so 2x is some constant and y 2x, right? So these are the same. So partial u, so half the conditions is met. We have computed partial u or partial x and partial b or partial y, and they come out to be equal. This means the first condition is satisfied. Let's now check the second condition, partial u or partial y, whether it is equal to minus negative of partial b or partial x. Right. So let's check this. Partial u or partial y is minus 2y. X squared would be treated as a constant, and partial v over partial x is 2xy. 2y would be treated as a constant times x is 2y. Right. So since partial u over partial x is equal to partial v over partial y, this condition is satisfied, and partial u over partial y is negative of partial v over partial x. This condition is also satisfied. So this means Cauche Riemann equations are satisfied for this example. This means it is differentiable everywhere. F of c is differentiable. Is differentiable everywhere. How to find its derivative? That's simple, using this formula. So we have checked that it is differentiable, and now we're gonna check whether we are not now we are going to compute its derivative. So f prime of c is partial u over partial x is 2x plus j times partial v over partial x 2y, j times, where j is iota. Right. So this is how we compute f bar of c for this example. First we have established that this function is differentiable, and once we know that this function is differentiable, then we can compute its derivative using this formula. Right. That's all for this example, and in this lecture I have one more example for you. Example number 2. Maybe this was example number 1. So I have one more example for today. F of x is given to be e to the x cos y plus j sin y. So it's not f of x, this is f of c, the complex number. So it's a complex number, it's a function of a complex variable z. So f of z can also be written as, if you multiply this e to the x inside, this is e to the x cos y plus j e to the x sin phi. This means this is the real part, this is the imaginary part. So u is e to the x cos y and v is e to the x sin phi. Now it's the time to check whether this function is differentiable, and we'll do that by checking using Cauche Riemann equations. So the first check is partial u over partial x. It should be equal to partial v over partial y. So partial u over partial x is e to the x cos y. Cos y is written as such, and e to the x has a derivative e to the x. And partial v over partial y is e to the x is treated as a constant and is being multiplied, so we'll write it here. Sin y has a derivative cos y. So partial u over partial y comes out to be partial v over partial y. This means the first of the two equations is satisfied. Let's now check the second equation, partial u over partial y. Partial u over partial y, e to the x written as such. Cos y has a derivative minus sin y, and partial u over partial x is sin y treated as a constant being multiplied, so write it as such. E to the x has a derivative e to the x. Right. So now we have partial u over partial y is equal to negative of partial v over partial x. This means the second equation is also satisfied, and we are done. This means this function is also differentiable. This function is also differentiable. So once we have established that it is differentiable. Now we are going to find actually the actual derivative. Now we are going to find the actual derivative of the function, and that is this using this equation f prime of z is partial over partial s plus j partial v over partial x. So partial v over partial x is e to the x cos y plus j partial v over partial x is e to the x sin y. So this is how we compute the derivative of this complex function. Right, now that's all for this lecture. In the next lecture we'll study more about complex variables and their functions. Thank you.